past decades, lots of scientists have made lots of efforts to group elements that were discovered at their time into families that would make the study of these elements very easy. Dobrina made his own contributions. Newland made some contributions too. Then finally, the breakthrough came in 1869 when Mendeleev, a Russian scientist, came up with what he called the periodic table. Mendeleev arranged elements that were discovered at that time according to their increasing atomic mass. Then very importantly, he discovered that some properties kept recurring along this arrangement. Mendeleev left some gaps in his periodic table that should accommodate elements that had not been discovered at that time. Later on, elements like scandium, gallium, and germanium were discovered, and they fitted perfectly into the Mendeleev's periodic table. Not only did he leave the gaps in this table, he also predicted the properties he expects these elements to have. Don't forget that at the time he was making these predictions, these elements were not discovered. Other scientists later on discovered faults here and there and modified Mendeleev's periodic table to give us what we now have as the modern periodic table. The modern periodic law states that the properties of elements are a periodic function of their atomic numbers. This is in contrast with Mendeleev's periodic law, which arranged elements based on their atomic masses. If you look at the elements in the periodic table, some are metals, some are non-metals. Actually, the metals constitute a larger percentage of the periodic table. The non-metals towards the right end, constitute a smaller portion. Then in between the metals and non-metals, there is a zigzag pattern. There is a zigzag pattern that aligns the metalloids. These metalloids are elements that have some properties of metals and some properties of non-metals. They are sometimes called semi-metals. Okay, so that is about that. Then we also can classify the periodic table based on the groups of elements. Like I mentioned earlier, the vertical column of the periodic table, the vertical columns of the periodic table represent the groups. And at your level, actually there are two different groupings. There are ordinary groupings, that's the group 1A, group 2A, group 3A, group 4A, which are the groupings that we are going to talk about today. Then there are other groupings that are for transition metals we are not going to be discussing now. So today we'll be talking about the group 1A, group 2A, group 3A, group 4A, group 5A, group 6A, group 7, and group 8A. Group 8 are also called, can also be referred to as group 0. Now, very importantly, you need to know the names of these groups. Some of these groups have their special names. For example, group 1 metals are called alkali metals. Group 2 are called alkaline earth metals. Then group 7 are called halogens, and group 8 or group 0 are noble gases. Okay, these are noble gases. Now, as for the horizontal rows, that's where we have the periods. And in the periodic table, we have 7 periods. Okay, now the elements in the period have the elements in the same period have the same number of shells. Elements in the same period have the same number of shells. Elements in the same group have the same number of valence electrons. Take note of that. Elements in the same group have the same number of valence electrons. While I say the elements in the same period, that's the horizontal rows, all the elements within a horizontal row have the same number of periods. For example, period 3 has sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. All these elements are in period 3 and they all have 3 shells, 3 electron shells. Okay, they have 3 electron shells. So then all the elements in the same group, like I said, have 1 electron in their valence shell. For example, in group 1 we have lithium, sodium, potassium, rubidium, caesium, and francium. Now, all these ones have only 1 electron in their valence shell. If you go to group 2, you will have beryllium, magnesium, calcium, strontium, barium, and radium. All these have 2 electrons in their valence shells. Now, if we go to the noble gases, that's those that have complete shell. The noble gases have complete shell. Their shells are complete. We have the first member is helium, then neon, then argon, then krypton, then xenon, then radon, and so on and so forth. So all these ones are noble gases. Okay, so the groups, members of a group have the same number of electrons. Members of a period have the same number of electron shells. Then we'll also look at the block. The blocks of elements, blocks of the periodic table. When we write the electronic configuration of elements using the SPDF electronic configuration or SBTF connotation, we have elements that end with S. For example, we have sodium ends with 3s1. 3s1. All elements that end with S like that, S1 or S2, are in the S block of the periodic table, as you can see. Then the S block of the periodic table. An S block of periodic table constitutes groups 1 and 2. Groups 1 and 2. Then all the elements whose electronic configuration end in P, P1, P2, P3, all the way to P6, all those ones are in the P block of the periodic table, as you can see there. And those, of course, include groups 3A to group 8A. Okay, from group 3A to group 8A. Then there are special elements as the D block elements. Those are elements whose electronic configurations end with D, D1 to D10. All those ones that have the electronic configurations ending with D are, of course, in the D block. And that is where we find the transition metals. And of course, we have the F block also, where we have the inner transition metals. Okay, so the transition metals and inner transition metals, we may talk about them briefly later on, not now, not at this level. We'll talk about them much later. So that is that for the block categorization of the periodic table.